Dear students, today we will introduce Lab3 P1NQ implementation. We have three parts in this lab. The first one is AXS stream interface. The second is the bit stream generation. The third one is P1NQ overlay and implementation. Before we start today's lab, let me first introduce what is the AXS stream interface. The AXS stream interface is the advanced extensible interface. It is part of the ARM advanced microcontroller bus architecture. So it is a parallel high-performance synchronized high-performance multi-master multi-slave communication interface mainly designed for the on-chip communication. This interface is used for the processors to control the external IPs. Okay, let's start with today's lab. Here we will use the Windows. Let's first open the Vivado high-level census 2019.1 command promote. Then let's change to the Lab3 directory. Let's create a new Vivado high-level census project by typing the command. We have used this command in our previous Lab 1 and Lab 2. I think most of students are very familiar with these two commands. Okay, next we will open the project using the Vivado high-level census GUI and using the command here. Let's open the C source code matrix multiply.cpp and make it visible in the information pane. I think you are very familiar with this code. This is the matrix multiplication we studied in the Lab 1 and Lab 2. Next, in the derivative type, we select the top level function, matrix multiply, and right click and select the insert the derivative. Later in the derivative editor dialog box, we activate the derivative drop-down menu at the top and select the interface and the mode as ESE let, and then click OK. We select interface mode, select ESE light. OK. Then similarly, we repeat the above for ports A, B, and RES. OK, then we collect and run the synthesize to button and to synthesize and design to the RTL. OK, everything goes well and no error is reported. When the synthesis completes, let's use the run C and RTL co-simulation to launch the co-simulation dialog box, and then click OK to start the RTL verification. This is similar to what we did in the Lab 1. the code simulation is finished. Let's select from the solutions to export the RTL. Okay, the exporting RTL is finished. Our next step is to generate the bit stream. This time we will use another software which is called Vivado, not the Vivado high-level synthesis. Let's open Vivado first. This one. Okay, let's create a project. And we will select the RTL project and choose the same board mentioned before. Yeah, we can type a name for the project. We select the RTL project here. We keep connecting next. Okay, here please note that we need to select the right board we have. So here let's go to our file to look at which board and also which chip we are using. Let's look at the Lab3 and look at the TCL file, which includes the constraints and the processor and board information. Here we can find that we are using this processor, this is the name of the FPGA we are using. So let's go back to select it. Okay, this one. Let's connect the next and finish. Then it will correct the Vivado project. Okay. Sometimes when the processor and the boards which we are using is not listed in the Vivado software, we need to update the repo and maybe even to manually add the board. But here, the board and the processor we are using is already included in the software. We don't need to do that in our lab. Okay, from the Project Manager tab, we select the IP category and then we will try to add the repo. Here the repo is not the repo for the processor chip or the FPGA board. The repo is that the repo for the IP cores we have created use the Vivado high-level synthesis before. add repo. Okay, here we need to find where we have generate the Verilog code from the high-level synthesis which we did before. Here, let's see this. So in our current design, the IP folder is under solution 1 and MPL. Like this. Then we select it. Then it will report that there is one IP core, which is the matrix multiplication which we created before, and we pass OK. Now we can see that there is a user repo which has the Vivado high-level synthesis IP, which is the matrix multiplication. Then on the IP integrator type, we create a new block design by selecting create block design. Here we can type in the design name. Here we use the default one. Okay, here. Then let's select the add symbol and search for the ZYNQ or PYNQ processing system. We select the add symbol. We type in the NQ processing system and add it. The ZYNQ processing system is a microcontroller which is used to control the our matrix multiplication and communicate with it. Okay. Then we will add the matrix multiplication IP designed by ourselves. Okay, let's do this. Let's do it here. We have already added the matrix multiply, and here this is the matrix multiplication we designed with the high-level synthesis. And this is the ZYNQ is the microcontroller to communicate and control this matrix multiplication. Yeah, sometimes if we didn't use this part, we need to change to this part, but we have already selected this board when we create this project, so we don't need to do anything here. Then we run the block automation and run the connect automation. Let's run them one by one. First, run the block automation. We use the default setting. Okay, this step will automatically generate the ZYNQ processing system, and then our next step is run the connection automation, which will automatically connect the ZYNQ processing system with the matrix multiplication. Okay. Here we can see they are all connected. Oh yeah, here we didn't use the interrupt here. So our next step is on the source tab from the diagram window, right click on the design 1 with the design1.bd and select the create the HDL wiper. Here, create HDL wiper. We can let the Vivado do it for us. Yes, we can let the Vivado do it for us. And after the wiper is created, select the generate bit stream for the final processing step on the Vivado. Here is the generate the bit stream. Generate the bit stream will take maybe a few minutes. Let's do it. Let's say that it's running multiple blocks. So by collecting the design runs, we can see if there are still tasks running in the Vivado. Let's wait for a while for the bit generation to finish. Here we can see it's running on the right top. can see this task is began to run. Okay, we have finished generating the bit stream. Okay, we can export the bit stream from the file. Export the bit stream file. The bitstream file is the binary code which can be directly running on the FPGA board. Okay, we are almost there. And here we can see something that how to use this how to operate this bitstream generated from our previous steps. Let's open the address editor tab. And the processing system can be expanded to show the address to each block. Let's open it. Let's see. Here, we can see that we can see the address of this matrix multiplication, and the address is the register used by this matrix multiplication. By writing to these registers or reading from these registers with this address, we can directly operate on this matrix multiplication. Here, another important thing to list is the address for each signal on the Vivado high-level sensor generate block. Let's take a look at it. To check the files with all the information needed, do the source design. Let's do this one by one. Source. Let's select it. Wiper. Okay, let's look at this. Let's make it a little bigger and open it. Here we can see each signal of our design matrix multiplication is connected to the processing system through the ESE interface. Let's look at some example here. Didn't want to go so deep. Let's look at some details of this. We can see for example, for the int A is connected to the ESE interface, B and also the RES. Let's open the processing system, which is the microcontroller used to control the matrix multiplier. Here, after we open it, we can find that each address is here. For example, the memory A, which and B and RES, the length of this variable and how many bits it takes. Up to now we have finished the start from the high-level synthesis, starting from the C-level code of the matrix multiplication, which is here, and then we do the high-level synthesis and generate the Verilog code, and then we use the Vivado software to pack this Verilog code as an IP. We add the ESE stream interface to this IP core and then generate the bit stream. Finally, we will upload this to the FPGA board and try to execute it. This will be how to run this in the FPGA board will be described in the future labs. Here we want to give some hints for the future labs. We not only need to copy the bit stream, but we also need to copy the .tcl file, which describes the constraints for the hardware together to the PyNQ board, and later we will use the Jupyter notebook to execute this bit stream we generated. Okay, that's all for today's lab. Thank you.